Welcome to the RAPIDS tutorial. As you know, we're all experiencing joy with the network here, UT guest. So if you if you do have a personal hotspot that you can use, please try to use that. Otherwise, you can try to use or a VPN. If you have a VPN, that'll work. If you don't have either of those, you can try connecting to my personal hotspot, which I've changed to SSID Rapids within the password Rapids123. I've hit my Google file limit, so this is all on them for the time being. So let's hope it holds up, and let's try that. So it works. Okay, yeah. Let's see if it works with 70 people. Okay. Sure. Yeah. NG and
G, capital G.
So the Jupyter password is Rapids, lowercase.
Lower N, OSIS. And then capital P.
oh, Pixel. Okay.
Also, if you don't have a sticker with an IP, raise your hand. Sorry. So there's 1, 2, 3, 4 people. So we need at least 3 more.
I'll write one. And you didn't do 1 to 9, right? Alright, we'll get to the other of you in a second. Peter, write it down. Oh, he has it.
It works.
Yeah. You want to make sure your phone's plugged in?
Yes, I will plug in.
In the back, I think. I'm writing 1. We will have 2 more.
But I think I have like 5 gigs or something.
Yeah.
I don't find anybody else using it, but
Yeah.
Yeah, sure. Yeah, disable anything else that'll be sucking up your bandwidth if you're connecting.
yeah, anyone who connects to mine, don't stream videos at the same time. You're probably going to run out of bandwidth.
All right. Should we go and get started?
Yeah.
All right. If anyone, once you have an IP address, if you're still having issues getting connected, please raise your hand and someone will come around to try to help you. Got a couple of people in the back there. So just as a couple of housekeeping items, the way we'll get started is we're still getting a few more IP addresses, so we'll bring those to you shortly. What we're going to do first is have kind of a brief introduction to what is Rapids, and then we will go into the actual tutorial content. So Jupyter notebooks are coming up, which is great, and you'll start using them after we get through this introduction. So my name is Randy Gelhausen. I'm from NVIDIA. A couple other NVIDIA folks we had today is Nick Becker, who's right there helping. Dante is over there helping as well. So keep those hands raised if you have issues, and someone will come around to help. So before we get started, does anyone in the room have a lot of you used big data stacks in general, like Hadoop or PySpark or Dask? It's pretty familiar to a lot of people in here. Okay. So one of the ways where we got started with Rapids is essentially seeing that for a very long time, for like the last 10 years plus, one of the ways which people do large-scale data processing is to use Hadoop. And one of the things that is really great for is handling large distributed files. But one of the fundamental downsides of working with it is, at least if you're using the original MapReduce paradigm, is that you had to read from HDFS, run some processing, and the result of each stage of a job was going to have an I/O barrier and write back to HDFS. So if you were doing something like, let me read a bunch of raw data and filter out some records that are invalid or have missing data, okay, great, let me save my results back. And at every stage of your job, you're going to have multiple I/O barriers, at least 2 I/O barriers. So if you're doing something reasonably complex at all, like filtering those records and then joining, say, like transaction IDs to customer IDs or metadata, and in this case here, you've got like a 3-stage pipeline, you're going to end up with 6 I/O barriers, which is really annoying. So along came Spark, which everyone knows by now if you've paid any attention to what Spark does. It tries to hold everything actually in memory, so you can eliminate a lot of I/O barriers. So you end up with both a little bit faster processing, given that it's all just reading straight out of memory, as opposed to reading from HDFS at each stage. But you also end up with a reduction in the total amount of writing I/O barriers after each stage of the job. So you can get pretty good improvements from doing that, right? Like obviously, if you're going at memory speed instead of using disk speed, that can be pretty nice. But as you can see from these bars here, which are obviously not to scale, well, we can do better. So where we'll go is even on the Spark side of things, and this has been true since I think around 2012 even, there were some studies that came out showing essentially the amount of time that it took Spark and Pandas and any other actual I/O libraries when you're reading CSVs or Parquet or even org files, things that are nice and columnar or compressed. There is a lot of time spent just trying to read things off of disk, and then once you've got bytes off of disk, actually converting those bytes into something that is a JVM-friendly object if it's Spark, or even Python-friendly objects if you're just reading directly into Pandas or even in NumPy. So there is a lot of places in Spark, as well as in Hadoop, as well as in lots of other PyData libraries where you're really significantly CPU bound. Not just at I/O, but actually doing any filtering, doing any aggregations, doing your standard data transformation processes. So NVIDIA saw this, obviously, and having these nice big graphics cards that are great at drawing pixels on the screen, well, they're also pretty great at doing all kinds of normal data manipulation. So how can we do better? One of the things which NVIDIA is really trying to do with RAPIDS is focus on what we call an end-to-end pipeline. If you're an NVIDIAN or if you've worked a lot with NVIDIANs, you hear us say end-to-end quite a bit. What that actually means is not just taking some data off of disk and then processing it a little bit and writing it back to disk and passing it to some other application. For a fundamental reason with GPU architectures, we actually try to do the entirety of the processing all inside the GPU. And the reason for that, essentially, if anyone, has anyone here actually worked with, say, CUDA applications before or done significant like image analysis or using deep learning algorithms where you've got to pay a lot of attention to batching and batch sizes? The fundamental reason for that, essentially, is, as you all well know, if you've used it, is copying data onto the GPU has a significant latency penalty with going over the PCIe bus. We always just affectionately call that the PCIe bottleneck, so it's not PCIe to me, it's actually PCIe bottleneck. And if you were doing deep learning or actually other early stage traditional analytics work inside the GPU, what you end up having is people copying data onto the GPU with the first application, processing some results, and then paying the same kind of HDFS I/O bottleneck, just the PCIe bottleneck now, copying data back onto host, and then passing it downstream to some other application. And that's great, the Unix philosophy of have one simple application that does one thing and then passing it off to another tool works for a lot of cases. But when you really are paying a lot of attention to doing efficient compute and doing it at very large scale, sometimes that actual paradigm falls apart. And nowhere is that more apparent than working with GPUs. So what we started doing, the core idea behind RAPIDS initially was how can we really eliminate that? How can we eliminate the need to copy stuff back off of the GPU, back onto host, and then start up new applications and copy it back over? Well, NVIDIA obviously is paying attention to what's going on in the analytics ecosystem. A lot of us are familiar with Spark, a lot of us are familiar with Hadoop and been using it for quite a while. One of the other projects which has really come to the forefront lately, thanks to the efforts of Wes McKinney and Eve and quite a few actual people in the community, is this project called Apache Arrow. Arrow, long story short, is a lot of things, but one of the fundamental aspects that it has is defining a standard for representing data in columnar fashion in memory. That is true for host-side applications, and what we've done with RAPIDS is actually to implement a mostly arrow-based memory model on the GPU as well. So RAPIDS itself actually has quite a few different components that all interact with this arrow model, but the idea behind actually us following this arrow model is so that anyone else whose applications can read and support the arrow format can actually read directly from pointers on device to device memory rather than have to copy things back and forth. And I'll say a little bit about this further on, but if you're using RAPIDS, and I'll say what that is, that's great. You know, again, things are nice and integrated and things work with GPU data frames back and forth from one library to another. But if you're actually going to go use something more like PyTorch, there's nice ways to pass data back and forth between RAPIDS libraries and PyTorch, as well as things like cuPy and Chainer and anyone else who supports these kind of standard memory formats. So kind of jumping to the conclusion of where we see this data processing evolution going, not just eliminating I/O bottlenecks, but eliminating PCIe bottlenecks and eliminating actual bottlenecks of serialization and deserialization between libraries that are operating on in-memory data, ends up resulting in not just 25 to 100x to start, but then you get quite a few additional iterative improvements. And overall, we see it's a little embarrassing to even say like 50 to 100x numbers, right? Because, okay, when someone comes in and tells you you've got 100x improvement on something, it's like, A, do I really believe them? And B, maybe the original application that you're comparing to is something that was written in a poor way. But we actually have quite a few benchmarks that we show we get anywhere from 50 to several hundred speed up, or several 100x performance improvements. Like all things, though, it really depends on the data and it really depends on what you're doing with the actual application. But long story short, your GPUs essentially have quite a few threads and have very high memory bandwidth. So if you can actually have applications that are able to use common memory formats and are able to pass references back and forth between various APIs, you can get huge, huge, huge performance improvements. So without further ado, you've heard me say RAPIDS a few times. Well, what is RAPIDS? Here essentially is our stack. So like all problems in computer science, the hardest thing is actually naming. This is no different for NVIDIA. NVIDIA had a thing that was started about anywhere between 10 to 12 years ago. It's called CUDA, Compute Unified Device Architecture. Has anyone here actually worked with CUDA or written CUDA code before? Okay. So I like to joke, and I say this in all my presentations. I got started with CUDA when it was CUDA 1.0, and that convinced me that I did not want to work with CUDA. So I joined NVIDIA about a year and a half ago, and what actually convinced me to join was looking at the Numba project, which is obviously a Python library that will let you do just-in-time compilation of Python code, custom Python code, down into vectorized operations that can happen on the CPU. Numba also has a numba.cuda.jit extension, so you can take Python code and have it be compiled down into something that will run on the GPU. So to me, what RAPIDS is really about is enabling Python layer applications to write familiar Python code that takes advantage under the covers of GPUs without forcing anyone to know anything at all about CUDA, which is a glorious achievement, in my opinion. I don't ever write C++ anymore. I now am focused entirely on writing Python. So what that actually means from this hard-to-name perspective is we have cuDF, we have cuML, we have cuGraph. cuDF is the CU from CUDA, Compute Unified Data Frame. Essentially, that means a GPU data frame. So you've used Pandas, you've used Dask, you all raised your hands when I asked about that. cuDF is actually following and implementing the Pandas data frame API, but running on GPUs. So if you were to check out the cuDF GitHub repo, the very first example that you'll see is actually just reading a CSV and then doing the same kind of normal aggregations and summations and mean computations to figure out, what's the tip percentage for people who leave certain tips at diners. So cuDF is a GPU data frame. cuML, CUDA for machine learning, essentially this is following the scikit-learn API, but also just GPU accelerated. cuML and cuDF, like all things here, have nice ways to pass cuDF types into cuML, just like you can go from Pandas data frames into scikit-learn models. We've got cuGraph, which is we're really kind of just getting started with our graph analytics packages. There's quite a few graph libraries out there, Hornet and NetworkX and a couple of other things. We're working on defining which APIs we're going to support there, but you can do things like PageRank, Jacquard similarity, etc. And then last but not least, these two boxes over here on the right, I talked briefly about being able to integrate with PyTorch. That also includes anything like MXNet and Chainer. Actually, anything that really supports DLPack. If anyone's familiar with XGBoost, it came from the DMLC community. One of the other aspects that DMLC has is the DLPAC format. It's a tensor format. So anything that is a cuDataFrame can go directly to the DLPAC format and then therefore go into PyTorch. So I've actually seen quite a few applications where people do a little bit of pre-processing, just use cuDF CSV reader or ORC or Parquet readers to accelerate the read of bytes off of disk into GPU memory, do a little bit of filtering out of records or filling null values if you've got some specific ways of imputing missing values, and then passing over to PyTorch. People have gotten anywhere from 20x to 50x faster improvements in deep learning pipelines just using some of the aspects of RAPIDS to do a little bit of pre-processing. And then we've got cuX filter, pronounced cuCross filter. We're early in the visualization side of things. There's obviously lots of work when you're going to go use something like Data Shader or Bokeh or any one of your visualization libraries. If you kind of live want to do some selections and say I want to select these ranges, well, if you're operating on millions or even billions of data points underneath, you don't want to have all that stuff happen client side in your browser. Instead, you actually, with cuCross filter and some of the other visualization components that we're doing, can pass the filtering and other pre-computations down to the device to just have images be rendered on your screen much faster and more efficiently. So that is a really fast introduction to RAPIDS. The whole idea of RAPIDS fundamentally is about providing speed of GPUs using familiar APIs. So Pandas on GPUs is cuDF, scikit-learn on GPUs is cuML, and then we've got graph analytics and a couple of other things. So with that is a really whirlwind introduction. And now I think we're going to start looking at the tutorial content, which, is anyone still having issues getting into their actual Jupyter instances? Please keep your hands raised and someone will come around and check it out.
So not have an IP address. Also raise
Probably. So just a couple of points here. So yeah, one, apparently the hotspots only allow 10 people on. So, and there's way more than that in the room. So if you have a hotspot that you're willing to share, that'd be great.
Hotspot. If you need it, Nick Becker's iPhone, the password is the same as it's written.
Well, yeah.
RAPIDS123.
RAPIDS123. Okay, we'll write that up. Also, apparently Tor browser works, and
Any VPN.
and any VPN will work. Most VPNs will work. Some VPNs will work. No VPN. No. Also, I wanted to introduce myself and Aaron. So I'm Anthony Scopatz, and this is Aaron Muir, and we work for Quansight, and we're also helping out with this tutorial. So feel free to flag us down and ask for our help as well. So, okay, so we'll hand out the remaining IPs.
Who needs an IP?
Yeah, who needs an IP will raise hands, and then if you're still having trouble on hotspots after this next couple of rounds or VPNs, let us know and we'll work with you. So, yeah, okay. You wanna? Yeah, you can go to them. And then you're going to the next tutorials. Yeah. Or, yeah. Okay. Thanks for your patience, everybody. It's been very fun with the network here today. Oh, yeah. Oh, okay. Okay, perfect. And apparently we're going to get a secure Wi-Fi soon to deal with this, so that's nice. Yeah, and I think... And I think Nick's gonna take it away soon. Apparently, yeah.
I'm working also on other solutions just in case.
Okay, yeah. All right.
Awesome. So I'm just going to do that very briefly.
I think I'm just going to absorb.
Okay, so welcome again. Thanks, Randy, for an overview of the RAPIDS ecosystem, the RAPIDS project. I know we were just going around. Does anyone currently not still yet have an IP address? Please raise your hand. If you, looks like we're good, but if someone comes in and is confused, could you just let them know that they should raise their hand and flag one of us in case we don't catch it when they walk in. Is everyone able to access a page that looks like this? No. Okay, thank you, very perfect. So we'll work on trying to help you get settled with this. But so when you look initially at this,
Is there a way we can turn these lights off? It's really
probably, yeah.
I'll futz with it.
Good idea. Okay, so while we work on getting the lights turned off, when you go to these IP addresses, what you're actually doing is running in your browser an interactive Jupyter notebook that's hosted in the cloud. And so the first thing to do would be to click on this index.ipynb, which is, thanks, Anthony. Oh,
I think the middle one would go on. Perfect.
awesome.
nice, thanks. This is the index notebook. And so the, in case someone's not familiar, the ipynb extension is just the Jupyter notebook file extension. And so this is a very basic tutorial that's just going to cover a few things. It's hopefully going to leave you at the end of this 3.5, 4-hour session with an overview and a pretty solid understanding of what it means to write code in the RAPIDS ecosystem. And for those of you who are familiar with Python, it's likely going to be fairly familiar if you do analytics-related work in Python, which presumably many of you do. That's why you're here, hopefully. And so it's going to start with this index notebook, which gives you essentially an overview of the different notebooks in this repository. So you can see there's an introduction notebook that you can click on with this hyperlink. You, of course, can also navigate, if you're so inclined, to the notebook right here. But the hyperlinks will work. We're going to start with about an hour of content on the CUDA DataFrame, as Randy was talking about. And we're going to go through an introductory notebook that has, I think, about 7 exercises designed to help you get just a feel for what it means to write code that uses the CUDA DataFrame. And it looks just like Pandas code. And then we're going to shift to a new notebook that also focuses on what you can do in terms of writing your own functions to apply these kinds of custom logic and custom functions to CUDA data frames. And again, there's going to be a couple exercises that ask you to do things like create your own distance functions and create your own user-defined functions for various different tasks that the solutions are provided, but if you get stuck, but we encourage you not to cheat, at least not right away. Then we're going to take a brief break and move into cuML, which, as Randy said, is the machine learning library in the RAPIDS ecosystem. And it is based on scikit-learn, so it should look very familiar for those of you who are coming from that kind of background and experience as well. And then we'll end talking about cuGraph, which is a graph analytics library in the same vein as something like NetworkX, integrating projects like Hornet and others from Georgia Tech and UC San Diego. And so with that, the first thing to do is to open up the introductory notebook. You see I just clicked on the hyperlink right here, and it brought up this notebook. And if anyone has any issues with these links or anything like that, please raise your hand and one of us will come around and try to help you. And so you can see right away that this introductory notebook was created by one of our colleagues at NVIDIA named Paul Hendricks, who couldn't be here with us today. But so we encourage you to go through this notebook, and really the goal here primarily is this line right here to make sure that we actually have a GPU. When you run this line, you're running essentially a terminal command based on this little exclamation point. That is a standard command that you would run to essentially get a sense of what your GPU system is. And so if you don't see a GPU here, in fact, you should see this almost the exact same information as I do right now. You should see a Tesla T4 GPU. If this isn't what you see, please raise your hand. One of us will come around because you will need a GPU accessible for this tutorial, obviously. And so with that, that's really the goal of the introduction. But we encourage you to read it. Once you've read the introduction, you can go back to the index and feel free to click on this Intro to cuDF notebook, which will pull up the first notebook of the tutorial. As you go through it, you'll see that there's clearly various lines and Jupyter Notebook cells that you can run. For those of you who have less experience with Jupyter Notebooks, these cells are intended to be run in order. If you try to run the cells out of order, you may see something like this, where various things won't be defined, you'll get errors. If you end up running things out of order and get confused, that's okay. you might want to just go back to the top and start over. If you really get confused, you can actually restart your kernel entirely and then start from the top again. This is a fairly small notebook, so actually starting from scratch and running the cells will only take about a couple of seconds. If there's any questions right now, that's great. We'd be happy to preemptively answer some. If not, please feel free to ask questions by raising your hand as you go through the tutorial. And you'll see the exercises are delineated with exercise 2, and there's a cell for you to write in. You can also create cells in the notebook if you're so inclined by actually going to the edit. No, well, not sure exactly where it is, but I'll find it. You can click on the side and click A to go above and click B to go below. I'll find where it actually is in the tutorial. But if you need more space, you can click on the side here and click A and B to add a cell above and below where your current cursor is. Okay, sounds good. If you finish in a period that looks like you're way ahead of your neighbors, that's okay too. Please feel free to go on to the next notebook, which again is accessible by the index notebook, which is right here. Please feel free to ask us questions, have discussion. If you have interest beyond the notebook in learning more about Rapids, we'd be happy to talk about it. But please feel free to move forward as you finish the notebook into the next notebook. But if you can, please hold off going to section 2, because before we talk about cuML, Dante is going to sort of give an introductory overview of that as well. Cool. Just for everyone to be able to hear, the question was, in the notebook, there is a section that shows how you can do things like query using the actual API method query. Is that because that is the preferred way of doing this versus just actually doing the more canonical pandas dot notation accessor and actually doing the query like that? The answer is no. It's just because we wanted to show that you can do both.
All right, hello everyone. So I think we're gonna go through the notebook as a group here. So hopefully this will all hold out and everything will work. And if you have any questions that you think would be useful to ask publicly, or even if you don't think they're useful, they probably are. So feel free to ask them. No, this isn't my laptop. So basically, we're just starting up NumPy in this first cell here and getting a random seed. Is everyone familiar with pandas already? Or is there anyone? Yeah. Okay. I think that is basically everyone, thankfully. Or if some of you don't want to admit to being familiar with pandas, that's your own business. And I won't call you out for that. So this is just showing a simple pandas example, right? So we created DataFrame with a key, with a couple of different columns here, key and value. And then you can do normal DataFrame-like activities like aggregate over a particular column. No big deal. The idea behind cuDF in particular is to try to match the Pandas API as much as possible. And so doing things like what we did in Pandas is very similar, right? Basically the only difference here is that rather than importing from Pandas, we're importing from cuDF. So this is the difference in terms of the API, right? Obviously under the covers, this is totally implemented completely separately. It's the memory here is all on the GPU. Oops, and someone is, I will cancel this, I guess. And we can get our data frame back out. So it's just very minor differences. And we can do the same sort of pandas activities that we would do as well. But those computations, again, are taking place on the GPU. Similar API, right? So we can create series. From series or other objects, we can create more sophisticated data frames. as well as you can also transfer data back and forth to the GPU and to the CPU using the from pandas and I believe to pandas methods. So here we had something that was in pandas in main memory on the CPU, and then we're shipping it over to the GPU by creating a cuDF data frame. Okay? Any questions on any of that? Yeah. That happens when you call that method, right? So that because you're literally saying like take this, put it over here, right? Any other questions? Yeah.
On that topic, so if you do operations when the data's already on the GPU, are those done strictly or lazily? Or do they batch up together, or is every operation done?
Sorry, can you just repeat the question?
Sure. Are the operations strict or lazy?
There in the actual cuDF library, there are no lazy operations. When you execute a function, the function executes. There's another library that we use called dask, which is not part of this tutorial, but we use that to do multi-GPU and things like that. Dask is a lazy library.
Yeah. Great question. Yeah.
A lot of scientists doing a bunch of text in your data frames. They're not doing math. The GPU acceleration is still going to be noticeable if they're doing a god-awful amount of text manipulation.
Great question.
Yeah. So the answer is yes. So the question is, if you're doing a lot of text manipulation on the GPU, is that still going to be accelerated? And the short answer is yes.
I have a good specific example. I was working on exactly that. I tried creating a series versus Panda of 3 million short strings, and then I just did a simple replace on it. In Pandas, it's 920 milliseconds. If I use cuDF and do the exact same thing, I get down to 100, so 9 times faster. But if I actually use a NumPy fixed length U4 type, I get down to 18 milliseconds.
Yeah, so David, just to repeat David's example here, if you take a short string in Pandas and a short string typed data frame and do a replace on it in Pandas, it's 900 milliseconds.
Yeah, 900 to 100 if I still use the object type, and down to 20 if I use the actual fixed length string.
Yeah, and then when you convert to the GDF, the cuDF data frame here, then it goes down to 100. And if you actually that's using the object type, and then if you use a NumPy D type of a fixed length string, that goes down to 18 milliseconds. So quick.
One thing to explain about that, when you're doing that, and you're going to call cuDF string replace, the very first thing that has to happen is it's got to copy that memory onto the device. And then when you call the CUDA kernel, which is underlying that string replace function, there's some overhead you call in the kernel. So the higher number of strings that you get, you basically should see amortized better performance over that longer list. And then further, this is why we make the point about end-to-end workflows a lot. If you were to call many of those string replace functions, the cost of transferring that data to the GPU to begin with is again amortized over the cost of as many string functions as you use.
Yeah, I'm just timing the operation.
Oh yeah, and that makes sense. And there's going to be a lot of cases where if you use like a NumPy operator on strings, it's going to be faster than say some small number of strings on the GPU.
Just to quickly add on to that, we also have built in our in real time, currently improving and expanding the capabilities to read data directly onto the GPU, so that you don't need to send data to the CPU, then copy it directly to the device in the same way. These GPU-accelerated data readers can be significantly faster depending on the data types, and it's obviously going to vary. But we're seeing some fantastic speedups with things like reading from CSVs, standard things like that. If you're interested in things like that, or looking at the entirety of the strings library, for which there are many different functions and methods beyond just replace,
Okay.
you can check out the documentation, and we can show you how to do that later at some point. But it's docs.rapids.ai, and there's lots of information about all the capabilities, and there's a fully featured strings library.
Yeah, great question. Great discussion on strings. So the sort of normal pandas inspection utilities are available as well. So if you're used to calling like dataframe.head or df.tail, those are also available. Don't get confused here. DF is still a GPU data frame. So you can inspect the data that you have. You can select columns like you normally would. You can select by label or do multiple selections. Ooh, let me execute that. This is all, should be all kind of very familiar. Wow, I will overwrite. I'm sick of this. This should all be sort of familiar to folks who use Pandas day to day. So, and if there are any questions on any of this stuff, just please stop me. So selections by index as well. Okay, and then, so this first exercise was to select only a certain number of rows from the data frame. And then, does anyone have a solution that they want me to type up here, or what did folks get? Come on, shout it out. Got to speak up. 4:9.
2 brackets and then 4 common 9.
2 brackets.
Like, bracket there.
Okay. Or 4 common 9. 4 common 9. Yep.
You need 2 square brackets.
Oh, 2 square brackets. Yeah, that's right. Nice.
Yeah, you have to use
iLock. Yep. There we are. All right. And then maybe. Nope. Oh, you have to print it. That's right. There we go. Perfect. Great. Okay. And was there? There we are. That's the answer. Boolean indexing, right? So this works similarly to how it does in Pandas and NumPy. You create a Boolean mask, and then you can index by that. There's the query method is also available, and you can pass these various queries in. So maybe we should actually print this. Where do you go? Function home? Okay. I'm learning a new keyboard up here. Yeah. So are there any questions on this? Should also be very familiar. Huh? Okay. So yeah, so we won't go through this exercise. There's missing data, features as well, just like in Pandas. There's the normal sort of statistics that are available as well. There's this apply map method, which allows you to apply a function to the data frame. And so that'll get moved over and applied as well. Oh, and here's all the string methods and everything. Since we're in the interest of time, does anyone have any questions on this notebook at all? Anywhere further down? Yeah.
What is the story of multi-index support? The group by operation looked like there was some support with the group by multiple columns, but set index doesn't work with multiple columns.
Yeah.
Yep. So currently we have very standard support for multi-index. It is not, as you notice, it's not perfect yet. It's a work in progress to make it fully featured. But we do have functioning multi-index support for things like multi-index group bys, hierarchical joins, things like that. But it's not fully feature complete yet.
But it's in scope.
Oh, it's very much it's in flight.
Yeah, I would say the thing to keep in mind here is that like the Pandas API is huge, and this stuff is getting better and improving all the time. So yeah, so it's not complete yet, but it's getting closer. So all right, any other questions on this notebook? Yep.
Are there particular Pandas API elements like on your wish list of things that I'm going to stub my toe on if I dive in on this? Where it's not there yet, we want to have it, so just something I should be aware of before I swap in PDF for Pandas DataFrame.
I guess like really, really complex, sort of more complex date time related things like resampling. and like time series resampling. We have great time series functionality, but things like resampling and that kind of functionality is not as in flight. Generally speaking, our goal is to be fully featured, and so if there's things that you notice that aren't there, please let us know. Or you can please let's just chat now and tell us what you want, and we can find out if it's there. But it's a publicly open source project. It's 100% open source. Development is on GitHub. You can see all the dumb things and smart things we say. And because of that, it means you can make feature requests, and we really listen to that, and that affects our development and understanding what users want.
Carol?
Is there a best practice that's emerged or is emerging for, I've got a Pandas library or project already done, and I want to move it to this?
Right. Yeah, so the question is that Carol's question is there a best practice for saying I have a Pandas library already built or Pandas tooling already done? How would I move to cuDF? So.
It's a great question. There isn't yet a best practice around that. Right now, the recommendation I think that we would give would be to import cuDF.
Check 1 2.
In addition
Hey
to
hey.
Pandas and
Check
do
check
the
check
actual
check.
replacement. There's work in the sort of PyData ecosystem.
Check
particularly
check
around
check.
NumPy
Check hey
NumPy,
hey.
which
Check
is
1
another
2.
GPU library
Hey hey.
for analogous things to NumPy and SciPy, about avoiding that problem by having them understand which functions to call, even if you write NumPy, but it's actually on the GPU. We haven't gotten to that point with the data frames. So, yeah.
Yeah, I would say from
Check,
personal
check.
experience, if you have just pure Pandas utilities, then it's actually pretty easy, especially if you're not doing anything super fancy like with a lot of multi-indexes or anything like that. If you're kind of a lot deeper into writing low-level Numba code, this ecosystem, this stack isn't quite there yet for perfectly interacting with that. But like Nick said, you know, it's very easy to open issues, and then those issues get addressed. So, yeah. Oh, yeah, perfect. Finally. So we got another mic, so if you have questions, we can actually just walk around with it. So, okay. I think that's it for this notebook. So
So
take it away, Nick.
the next notebook, and if you don't finish in time, that's totally fine. You can download these notebooks. If it's just a Jupyter notebook, you can download them. They're also
Is there a way to download this to local? Or
download the tool, as in the notebook or the actual libraries.
the notebook libraries?
You should be able to download the notebooks by saving the notebooks. If this doesn't work, then that is okay. These notebooks actually are public currently. They're on.
Yeah, there's a GitHub.
We'll post the
that we can
GitHub
show
that you can
later.
download them from at the end. So don't.
Take a Tesla too.
We can talk about that later. So again, if you don't finish, these are public, or if they're not fully public, they will be. That's the intention. And we'll give the GitHub link at the end of this. But the next notebook, which is the second of the two cuDF notebooks, is about user-defined functions, which you can get to from that index notebook by clicking the link here. We encourage you to go through this notebook and really understand, what's happening. There's a lot of valuable information here and good examples about how you can do things like write custom functions and apply them massively in parallel on data frames, which can be pretty significant speed up.
I was just going to ask, are any of you guys on the Slack channel for RAPIDS here in Scipy? Because some questions are kind of bubbling up.
Oh,
And so, I
Yeah,
don't know if that's maybe-
unfortunately, my Slack invite for this conference it didn't work, so I'm not. But other
Well, I could
folks.
speak on behalf of the Slack users.
Okay, yeah. Let's.
The conference?
Yeah, so for the Scipy 2019, there's like a
Yeah, the
workspace,
easily
and then
join.
within that, there's a channel
Okay.
that someone created for you guys.
Yeah.
That's so nice.
Yeah. Okay. Well, so I had a question. Somebody else had a question. One question for me is like about the configuration of this machine. Like this is a GPU instance. I did a little forensics on your IP address. The IP address that I have is on Google Cloud, so I assume this is a Google GCP, but I don't actually know anything further beyond that, like setting up CUDA libraries and what all was sort of involved. If once this is done, I'm going to have to spin up my own instance, and what your best practices or recommendations are. If you have any configuration files or some tutorial that I could follow.
I think Dante, if we could, Dante, if you want to come up and answer that.
But could you repeat the question?
All right, yeah, I'll repeat it a little faster.
These instances set up and
Absolutely.
How could you reproduce them?
Yeah, absolutely. So actually for many of the cloud providers, we have containers and images ready. But generally speaking, these are standard Google Cloud instances with, you can choose the amount of GPU and the amount of CPU resources you can use. If I remember correctly, we did this one with 4 CPUs. And 30 gigabytes of CPU memory, and Tesla T4s with 16 gigabytes of GPU memory. They're very easy to instantiate. Google already provides a bunch of default images if you want to start from scratch with Ubuntu 16.04, Ubuntu 18.04, or CentOS, which are the 3 Linux distributions that we actively test, and we can officially say that they work. And then you can our recommended method is on top of that, you just use conda to install your own packages. And that way you get the latest, you can get the latest cuDF, cuML, cuGraph releases, which for many projects, I would never recommend installing nightly builds. In our case, many times the nightly builds have bug fixes because we have a very fast pace of development. So that would be my recommendation, a standard Google Cloud or other cloud providers image with those versions of the operative systems, and using conda to install either the latest release or the nightly libraries that you're interested in. And that way they will also give you the correct versions of the requirements like Pandas, NumPy, the CUDA toolkit, the conda package, and other things.
And Dante, if you just want to click on that link where the highlights are,
that's
an example notebook that you can spin up for free on Google Colab, which is essentially one of their, it's like a hosted Jupyter notebook. And this will just work. It will let you do this in the cloud with complete ease.
And with a pretty nice GPU there as well.
A T4 GPU, which is the same GPU you're using currently in this workshop.
Which has 16 gigs of GPU memory, which not too shabby.
Also, where Dante just came from was RAPIDS.ai, which has a getting started section and actually followed like Torch's little Chinese menu of clicking what is my environment, what is my Docker version, etc. That'll give you a copy and paste command to either pull the container, or if you're going to run directly in your own conda environment, there's like all the conda install commands. So RAPIDS.ai, and then go to the getting started section. It has links to, do I want to install it directly? Do I want to try it on Collab? Do I want to go to like DataFrame, which we have on GCP?
Yeah, so here is the link that Randy is talking about. You can go here and kind of pick and choose what version of Rapids you want, and which method of installation, and it will give you the one line to try to accomplish that. If someone has these other open source libraries, they also have menu selections like this. We were very inspired by very beautiful visuals like this, so it's to make life people's life easier.
And so feel free to keep going with the notebooks. We'll be going around just like before to discuss things and ask questions and answer questions as they come up.
Yeah, then we'll have like a 15-minute break. Then we'll come back. I'll give you a brief presentation on the state of cuML and cuGraph, which have slight differences to the cuDF philosophy. I will focus it more on cuML just because I'm biased and I like cuML better. But don't say that officially. Both libraries are awesome. I have long arms, yeah.
Yeah, this doesn't slide.
Where's Beaumont?
I don't know. I was actually just looking around for it.
Let's see if we can.
I realized I really don't stuff. One other thing which may help you all, I think there have been several questions on, how would I do X, either in cuDF or in one of the Rapids libraries. So in addition to this rapids.ai website, a nice URL that's really helpful is docs.rapids.ai. For each of the Rapids projects, there's links to their Python API docs and their C++ underlying API docs. And we have links both to what is currently available in release packages as well as nightly doc builds. So docs.rapids.ai is a nice community gateway.
There was a question on Slack, which we are now in, and we'll be very happy to respond to questions in the Slack as well. Sorry about not being in it. The question was discussing or understanding how AWS or Amazon Web Services users can set up Rapids. And the answer is that you can do the same thing that's really happening here on AWS. There isn't that very, very nice thing. It's a test that you can do like on Google Colab, but it fully works on AWS. The question also sort of asked about recommendations for GPU instances. You will need to use an instance that is compatible with Rapids, and that means it needs to have a GPU attached to it that is at least the Pascal architecture or more recent, which I believe means you can use either one of like the P3 instances or one of the new instances with the T4s. I'm blanking, unfortunately, on that specific instance name. But we can find out that list. It's a list of a few instance types, and we can respond in the Slack to that question as well. So, and feel free to keep working. But so several of you have asked about these print statements in the haver-signed distance kernel portion of this notebook, which makes sense, and especially because when you run this kernel, there's no print output. And that seems kind of odd. And so it's briefly discussed right here. But essentially, this is the core of why these user-defined functions that we're applying are incredibly fast on the GPU. And so in CUDA, essentially, and essentially all GPU architectures, as Randy briefly mentioned in the beginning, we think of things as threads. And each thread does some unit of work independently from other threads. But there's actually structure. Threads are organized into blocks, and there's additional structure that it's not necessary to go into really beyond this, but you can learn more about things like warps and all sorts of different things if you're interested by Googling around for CUDA and GPU architectures. But essentially, each one of these threads is going to do one unit of work, and the threads are in a block. And so in this case, for example, in this actual example, you can see that we had a data frame of 1,000 rows, and under the hood, it's going to be optimally chunked up, and each block is going to get some data. And in this case, the print output that we have here is not something you see now, but if you were to run this on your terminal, you actually would see this print output. Every single thread is going to print out this print statement, and it'll be this variable that determines the thread's ID. Each thread has an ID, in this case just an X coordinate. It could have a Y depending on how you structured it. But each thread has an ID, which helps us know where in the final resulting output array the result of this computation should go. There's lots of different things like this. This is various attributes of the data and CUDA-specific things like the block dimensions and the block identifiers that help us keep track of where this data should go, or the resulting output should go. But essentially, the key here is to understand that each thread is doing work independently. They're organized into blocks, and this data that we had of 1,000 rows was chunked into 15 blocks. Now, you didn't know it was chunked into 15 blocks, and we didn't even know that. It was done for us. In the next section, we actually show how you can have control over that. But by default, this lets you automatically chunk it under the hood. And because we had 15 blocks, it decided to launch 64 threads. We, of course, could have launched many threads, but we only had 1,000 rows. And so that gave us 960 total threads. If we had 64 per block, 15 blocks, which means each thread is responsible for one row. Except not quite, because we had 1,000 rows and only 960 threads. And so that means that some of the threads needed to actually go through an array of 2 records. That's what you have here. This print output is just trying to give you a sense of what's actually happening within each thread. Each thread is doing some work. If it's only been assigned 1 record because it was one of the threads that didn't need to work on 2, then we're done. If it had to do 2, it had to do the first one and then the second one. Does that make sense? This is what gives it that incredible parallelism. Each thread independently operating with access to the full data it needs.
All right. Hello, everyone. So we can, I think what we'll do right now is we'll just ask if anyone has any questions on this notebook, or any questions about these UDFs or anything, and then we can go for a break. So no pressure on asking questions, but I'm sure there are probably some. Perfect understanding by everyone. All right, so if there's no questions, or if you have some questions, we can approach them after the break. Oh, yep, sorry.
Yeah, I remember from my CUDA experience that figuring out how to use shared memory was really pretty critical and didn't help. And that seems to all be hidden here. Is there stuff going on about using shared memory?
Yeah, all that stuff is being taken care of for you. There's a lot of different layers. So most of that stuff happens at the C++ layer. So there's a C++ implementation, or a CUDA C++ implementation of there's a memory manager, and then there's the arrow layout gets implemented and all that stuff. And basically what you're seeing at the Python RAPIDS kind of level is another wrapper around all of that stuff. So you don't need to worry about doing the memory management explicitly. Yeah. If you want to go down to the CUDA level and do all that stuff because you want to, you're welcome to. But yeah.
I believe you can. Numba.CUDA lets you access shared arrays if you want to do that inside of one of these kernels.
Yeah, so Aaron was pointing out that certain Numba.CUDA, and I think there's some other tools that you can use to share memory. You can basically get a view into the GPU memory from the different libraries that exist. So the kind of the right thing to do happens when you do data exchange between some of these GPU libraries.
Yeah,
I think that works with CuPy. Maybe.
So these apply rows. These are just Numba.CUDA kernels. So like anything that works in a Numba.CUDA kernel, if anybody's used Numba.CUDA before, will work in these.
Yeah, good question. Any others?
Actually, I guess I have one.
Okay.
I wanted to mutate an existing column, and I wanted to mutate an existing column, and I got the good answer that I should be concerned about a race condition if I do that, because in the kernel, it can't really assure generically the kernel is going to be nice and only refer to its own row,
right,
which is the particular case I had.
Right.
But looking at the kernel that you have, it doesn't really do anything to assure that it's nice either. Like the haversign kernel has out sub I and then being modified, but I could grab any number in that kernel, and it could be I+1, or it could be random number or something. How do you how do I deal with worrying about a race condition in that case?
Right. So this is probably a question for Dante. You want to? How do you worry about the race conditions in this haversign?
Yeah, if I write a nice kernel, then I'm only dealing with
So
one.
the way this one is parallelized with CUDA is that it's thread safe actually for CPU wise, so you don't have to worry about race conditions per se. That is taken care of you by the compiler. When you go for multi-threaded scenarios, CPU wise, to go for the multi GPUs, I'm talking threads, full CPU threads. When you would have race conditions, then that's when we leverage things like dask to do the distribution. But here, race conditions won't be an issue that you have to actively worry about.
I don't quite understand that. So like in this kernel that is in the example, haversign, or the other one, it modifies out sub I to be something. What if I were to change that to modify out I minus random int?
So usually the way though.
So I'm modifying a random row that's not my row, because I'm just doing an index into the out.
You're allowed to do that within a block.
Yes.
There's plenty of cases where you don't want to just modify your row. The problem is then if your other rows, your other threads are also trying to potentially modify the same thing, then you do have a possible race condition.
So just be careful is the advice, basically, which is, okay.
Yeah, I'm sorry, I didn't see the kernel that you were asking for. Sorry, but yeah,
That's reasonable advice. I'm not,
You can write it such that you use your thread ID and some other value in a column that you're using to guarantee that you're not going to be overriding someone else's result. But it's not super easy to do. So there are cases where you want to do that. There's also mostly cases where you don't want to do that.
okay.
You have to be very clever to avoid the race condition if you're modifying values outside your current thread.
Oh, yeah. So the answer I got from one of you folks is that I can't use the output value as an input, or I can't, mutate it in place because of the race condition concern. But then I realized that restriction doesn't actually solve that concern, which is okay.
Yeah, thanks, David. Great question. So I think if there's nothing else before the break, why don't we take a 10-minute break? We'll meet back here at 10:18. So, all right. And there should be food and snacks out there for the duration of our break. So, all right. Welcome back, everybody. Hope you had a pleasant little break there. So just before we get started on the second half of the tutorial, did anyone have any questions on anything in the first half? All right. Well, then I think I will hand it off to Dante here, and then he'll take it away.
Thank you, Anthony, and welcome back from the little break we had. The second half of our tutorial will focus on the rest of the RAPIDS libraries, or the rest of the main RAPIDS libraries. The idea with RAPIDS is to provide a full stack data science GPU-based solution. So to accomplish this, there are multiple libraries. The one we explored extensively already is cuDF, of course. The thing about it is that cuDF is probably the most complicated API-wise. It's essentially Pandas, which, as Anthony mentioned, it's kind of a humongous API to mimic. So there's a lot of functionality. A tutorial based on cuDF or Pandas can be very, very rich because there's a lot of little things to explore. There's a lot of little different ways to do things. When we go into the machine learning and network analytics world, things are very, very different. So that's what we will explore here a little bit, and we will provide you what is the philosophy behind cuML and cuGraph, and then we will go through a few notebooks that some of them are relatively basic, mainly focusing on creating a linear regression and seeing how to use cuML. And then we will go through a notebook that is kind of a very cool visualization based on a pretty cutting-edge algorithm called UMAP, which has been very popular for the past year, I would say, because it's kind of awesome, for lack of a better, more technical term. We will compare it against TSNE, which was another great algorithm, and we will see how different, how they can create very, very nice visualizations for very complex data sets. So I'm not sure you have seen this chart yet or not, but this has been one of our go-to charts. Why are we creating RAPIDS? Is to modify this data science cycle. As before joining RAPIDS, I'm being a data scientist. There was always the case of you would have a significant data set and you would try to create interesting operations on it, either ETL or either machine learning. So what you would do is press enter in your Jupyter notebook or run your Python script and go for coffee, go for something while your computer processes things. Even if you're using Spark to scale things, usually the problem would be large enough so that you could go for your nice cup of coffee. So we decided that so much caffeine in the life of data scientists is not healthy. So what we're trying to do is that you can, instead of going for coffee, you can run things faster and iterate faster. So just as machine learning is kind of an optimization problem, and the idea is to find the best models with the best parameters, the more times you can try different models, the better things you can accomplish. So that's kind of the philosophy we're going to and why we're doing what we are doing. That said, another thing that is pushing us strongly, or one of our main motivations, is to make things easy to use. For many years, it has been possible to use CUDA to do things very, very fast with GPUs. Same with before Hadoop, there were distributed frameworks that were relatively hard to use. Then comes Hadoop, comes Spark, things became easier. So what we wanted to do is something similar for the rest of data science with GPUs. Have a rapid stack that you just use the same code you are used to with Pandas, scikit-learn, network X, and all of a sudden things just work. Our pipe dream is you just change import scikit-learn for import cuML, and things just magically work. Of course, there are subtleties there. I would lie if I told you just need to change your import, but it's not as far as you might imagine. It's actually, sometimes it's possible, and many times it's just a matter of changing a few parameters, a few keywords, and things just work, or that's what we are working actively towards, and why we are iterating so very fast. So the RAPIDS solution, it's a multi-stack solution. I just wanted to talk a little bit about what's behind the curtain. Behind the curtain, what you saw here was the Python code, the Python API, which looked just like Pandas. At most, you saw Numba-style kernels, which you use as UDFs for parallelizing operations, but you never had to touch C++, you never had to compile, you never had to touch even Python, which we use heavily to connect our C++ and our Python things. So for distribution, of course, that means we have a lot of complications, and that's the reason we decided to leverage the Conda ecosystem as opposed to other ecosystems. Conda allows us to package our C++ side as libcudf for the case of ETL, and our Python side as cuML. So all of the stack that you see here to your left is all of a sudden two simple Conda packages, which, thanks to Conda facilities, is a single Conda install infrastructure. And that is also the case for the rest of the RAPIDS ecosystem, which, as we mentioned in earlier, it's based on the Apache Arrow specification. And that means we're interoperable with everything that follows that specification, particularly if they're on the GPU. If they're on the CPU, well, you need to copy the data at the end of the day. But the idea is we have a very complex and rich ecosystem that is simplified and made as easy and as approachable as possible. So just as I said for CUDF and ETL that has its libcudf package with C++ things that you never had to worry about as long as it's installed by Conda, cuGraph and cuML, we do exactly the same thing. We have a libcuML, which is just a typical C++ library that actually has its own C++ API for people that have more of a science code base that is already C++ and you could, or C based, and you could consume a C++ API. But also we have our CUDF, cuML and cuGraph APIs that mimic scikit-learn and cuGraph. That said, the stack is actually slightly different from what people might imagine, and I mentioned this since it's part of our vision to not only provide the ease of use of scikit-learn, it's also providing a C++ API that is rich that eventually you could use to build your own algorithms using what we have built already. So for example, we decompose all of our algorithms, dbscan, k-means, knn, into its basic operations. Not as basic as matrix multiplications, a little higher than that, like things like standard deviation, statistics functions, distance functions, and we name those ML prims, machine learning primitives. And then our algorithms are built on top of that. And all of those components are open source, and people can take them and do their own algorithms or use them in their own algorithms. And that's the vision we're pushing towards. Another thing that is coming is that those ML prims that I'm mentioning will also have a Python API. So at some point you will have CUDA optimized machine learning and graph analytic primitives, things like distance functions, anything that, even clustering algorithms, k-means, we treat it as a primitive since it's used in other algorithms that are bigger and more complex, or UMAP, for example, use knn. So even something as big as knn could be a primitive. You could take those components and create your own algorithm with way more ease of use than just writing CUDA code, which as someone that writes more CUDA code than he wishes for his own mental health, I would like, whenever we approach that level, to just live in the Python world, which is much, much nicer at the end of the day. Now, the CUDA libraries that we explore, people ask us always, why are you using CUDA? Why not use other platforms? Why not stick to CPUs? One of the main things that CUDA has is a very rich ecosystem already of legacy in quotation code. Code that has been optimized for many, many years, and it works very, very well. Things like cuSolver, things like Thrust, things like COP, they have very, very fast implementations. Of course, they're very traditional C++ APIs. They're great, but I don't stream the data, I have to call a cube function. You have to take care of a lot of pointers, a lot of flags. So those are the things that we're trying to optimize and or to make easy to use. And at the end of the day, you just see a scikit-learn, but a scikit-learn style API, but it goes all the way to calling all of these libraries constantly. Of course, those libraries form into what I've called ML prims, which include things like norms, eigenvalues, eigendecomposition, singular value decomposition, a lot of things. And those primitives are based either on the needs of our algorithms or on what people's interests are. So something that we like to promote a lot is people telling us what they want in GitHub issues, and then we can optimize our efforts towards that. A good example of this happening was UMAP, in which people wanted TSNE, but UMAP was showing amazing results, so we decided to focus our resources into having UMAP first. And it was the first GPU implementation available, actually. Now, that said, the status of cuML is that it looks something like this. We have a series of algorithms in single GPU. The ones that are gray are coming very, very soon. But just to give you an example of what is the type of cadence of release that we are aiming for, or the type of speed of development, is that in a single version, we're going to jump from something that looks like this with no multi-node multi-GPU algorithms, with 2 single-node multi-GPU algorithms, and a number of single GPU algorithms, into something that already has multi-node, multi-GPU algorithms, into improving the single GPU to have random forest inference, and that is in a release cycle that consists of 6 weeks. So every 6 weeks, we aim to increase our matrix of coverage of algorithms and operations from this to this. So as you can imagine, we're trying to be very, very ambitious. Of course, that means that we have nightly releases that have bugs, but those are the coding edge. So you want to try, for example, today you can already try our random forest, new random forest functionality with regression. You can install the Conda nightly package. The nice thing of how we have set up CI is that every time we merge a new feature to our code base, a new nightly Conda package gets generated. So you get the same cutting edge features as if you built the GitHub repository or you just install the Conda nightly package, which is one line instead of having to deal with CMake or Ninja, and also with setup.py and the requirements and having your Conda environment well, you might just as well install the Conda nightly if you're not going to do development per se. Now, another thing, and this is just a brief example, I'm not here to necessarily talk about benchmarks, but the other thing is that what we aim for is that subset of the ecosystem, which is kind of, there's not a great solution there. If you have terabytes of data, Spark and distributed algorithms do a fairly good job. You can have very, very big clusters, and you have a good API, and they can work. But if you, let's say, have a data set of 20 gigabytes, 10 gigabytes, Spark is a little overkill to have a cluster with Spark base. Pandas is kind of underkill because it tends to really scale. Pandas, scikit-learn, scaling beyond few gigabytes, sometimes they can have trouble. So for single GPU, one of the things we target is 10 to 20 gigabytes, medium-sized data sets, which are actually a significant number of the data sets that people face. You don't always face terabytes of data. Not everybody has big data. Sometimes you have medium data, and that is challenging. And the more data you feed cuML, for example, the more speed up you will see. In the examples, since this is a few hours tutorial and it's an introduction, I show you smaller data sets. So for linear regression or logistic regression, you might actually see that launching the cuML kernel might be even slower than running scikit-learn. And by slower, I mean by 2 milliseconds. That's usually a penalty that for small data sets might be too big. But when you go to bigger data sets, we can have 10 to 20x times the speed up of the comparable scikit-learn or CPU-based solutions. That said, there are algorithms where even for small data sets, we get really nice results. I will probably sound like repetitive, but UMAP is an example. You will have to process UMAP in the CPU in the notebook, and then use the GPU, and then I will let you just experience the difference in just the sensation. Now, that said, for the lower level things, we have decided to not reinvent the wheel as much as we can. If you notice, cuDF is Pandas essentially in the GPU. cuML is going to be scikit-learn in the GPU. But also lower level, we're trying to follow conventions that already exist. So we are following CUDA-like and C++ standard APIs design. So if you are interested into lower level and more optimized code, you will find our functions relatively familiar with things like using handles for resource reutilization. So for example, your handle can have a memory allocator that has certain characteristics for your hardware, and you don't need to modify our code to be able to use your memory allocator. You can just create a handle that plugs into that memory allocator, and all of a sudden, all our memory allocations use your memory allocator. And that's very, very important for things like interoperability with other libraries. So in the Python level, all of a sudden we look more familiar to the data science community and to what I would wish every library looked like, the scikit-learn API. So everything I talked about, all the primitives or the libraries actually get reduced to something that looks like this. Create your machine learning model or your machine learning object. In this case, we're creating a linear regression, ordinary least squares regression, and just call fit, and all of a sudden everything is done. The nice thing is that we are mimicking one of the best API designs, in my opinion, that there's in the Python community, scikit-learn. It's probably one of the best API designs. Super friendly, super nice. It's scalable. It grows with you because it has a lot of optional parameters. But if you don't care about optional parameters, it's as easy as tell it, hey, just fit our input, our predictors X to our response Y. So this also proved a little bit challenging to design the tutorial because all of a sudden it's just like a scikit-learn thing. Either we go very deep into the mathematics and when to use it, or things are pretty easy. You just create your data, create your model, tune a little parameters, and fit, and you have your model, which was actually very positive for me to find when we were developing this tutorial. That means we're doing an okay job at making things easy to approach. So you will see that the tutorials feel a little bit different from the cuDF that have a lot of little functions. Now, talking a little bit more into more advanced functionality that we offer, we already offer hyperparameter optimization. Since we are not only aiming to look like scikit-learn, we're aiming to be compatible with everything that scikit-learn is compatible. We are compatible with hyperparameter optimization that can work with scikit-learn. So for example, dask-ML has hyperparameter optimization. Also, scikit-learn already has hyperparameter optimization, and you'll see in the notebooks you can use the grid search functionality of scikit-learn to optimize your models with cuML estimators. You don't need to create your own custom things or expect that there's another library to learn to optimize your models. You can use already the ones you know. Of course, there's still a work in progress. Not a lot of models are yet compatible, but we're working into having every new model that we release to be able to be used with scikit-learn style functions. And finally, the last thing that I want to mention is one thing we aim a lot for is interoperability. We didn't want to reinvent the wheel, and that goes not only into mimicking existing APIs, it also goes into we don't want to replace existing libraries per se, we want to complement. So for example, if you have, let's say, a deep learning-based workflow, for example, a PyTorch-based workflow, and then you have all your results of PyTorch, and one very cool thing is to have your weights, and all of a sudden you want to visualize them somehow. Maybe you want to use UMAP to reduce the dimensionality, or PCA even, or some dimensionality. So you reduce the dimensionality of all your weights, and you want to visualize how things happen, which people have been doing lately. You can go from the PyTorch GPU torch tensors into cuML without necessarily creating a cuDF data frame or without having to do any more sophisticated things, and without memory copies and without inefficiency. cuML just takes things like PyTorch, CuPy, or anything that is compliant with the CUDA array interface. Just a little, probably quite a few people are familiar with it, but just a little like footnote here. The CUDA array interface is an interface that was proposed by the NumPy folks to have a similar interface to the NumPy array interface, so that if your library complies to that interface, you can do, for example, you can use NumPy kernels with CuPy arrays, and then go to PyTorch and then go to cuML, all without copy, and things are just compatible because we support the CUDA array interface, and we're trying to extend it so that it's more capable. And finally, the road to 1.0. There's a lot of things coming on, but the idea is to have a matrix or a function that looks more like this. All the algorithms have multi-node, multi-GPU capabilities, and we have more algorithms. Actually, here I forgot to put DSNE, and called Winters. I think it's not in that matrix. I can't remember. Oh, it is there. But there are a few other algorithms, and that's kind of what we're aiming towards 1.0, which could be version 0.12, 0.13. I'm not sure yet. That's kind of in the future, but with release cycles every 6 weeks, you will see us building towards this functionality. So I hope you have enjoyed kind of the overview. I know I focused more on cuML than cuGraph. That's for two reasons. Mainly, cuML is a little more mature, and also I'm more involved with cuML. So I'm very much in the open source world of cuML more than the open source world of cuGraph. cuGraph has a lot of functionality that is coming also. For version 0.9 has things like improved page rank, improved functionality, but I will talk a little bit more towards the last part of the tutorial when we go through the little notebooks of cuGraph. So now that we have done that, let's go into our notebooks, and now I will give you time to go through the notebooks. With TensorFlow, there's memory copies and inefficiencies just because they don't, as far as I'm aware, they don't fully support the CUDA interface. We're always working towards improving interoperability. So we work right now with that copy with the PyTorch, CuPy, things that already support the interface. Things will keep improving and will be more interoperable. That's the idea, that you could take also your TensorFlow workflow or your whatever new deep learning framework is. And then go without memory copies. Because at the end of the day, you can do always go back to CPU, then go back to the GPU, which could be worth it just based on the speedups, particularly, for example, for graph analytics. For machine learning, we get 10 to 20x typically, in average, when you have good amount of data. In graph networks, particularly against network X, which is kind of the de facto standard, we aim more for 100 to 500 times speed up. So in those cases, sometimes it's worth it, even if you have to copy the memory around. It's just based on the fact that network analytics are kind of more at the way, they exploit the massive parallelism GPUs very, very well. And there is not a scikit-learn. Scikit-learn, for example, is very good at parallelization when it has a parallel implementation. There's nothing similar in the Python ecosystem. You have to go to C libraries to get something like that. Before we go to a notebook, any other questions? Perfect. So as we saw in our, it's really hard to see my mouse from here, but as we saw from the beginning, we're going to go through a few notebooks. In here, in the case of cuML, we're going to go through 3 notebooks. And it's mainly 2 notebooks, in which the first one will go through a section of linear regression, which is essentially just the basics and fundamentals of cuML. For people that use scikit-learn constantly, you will find it very straightforward, I hope. You will tell me, why did you give me such an easy tutorial? That is my mission. That you say, hey, this is just like scikit-learn, I already know it. Then after that, we will go through an example of hyperparameter optimization using scikit-learn grid search. If you want any more details, if someone is not familiar with what hyperparameter optimization is, feel free to ask. Feel free to raise your hand, or feel free to ask for an explanation. I'm more than glad to go through any details that people are interested in, but I want you to get your hands dirty with cuML, to be honest. And then after that, there's a notebook exercise. There's an exercise notebook with logistic regression, which is to see whether you now dominate cuML. You will find that hopefully you will say, hey, this is kind of the same as linear regression, but I'm just doing a logistic regression. That is kind of my mission. And then we will go through the notebook of UMAP, in which we will see how some MNIST datasets are visualized by TSNE, and we will see how UMAP offers a different visualization that can be more useful to analyze data sets. That's a little larger notebook, and it takes a longer time to process, particularly the CPU UMAP cell. But feel free to explore the 3 notebooks. Most of the essential exercises have solutions. All of the essential exercises have solutions. For exercises that don't have solutions yet there, I have the solutions in the instance that I'm connected to, so we can gladly go through different solutions. The nice thing is that some of the exercises you can arrive at a different solution with different parameters perhaps. So feel free to start going through the 3 notebooks in cuML, and feel free to ask us for any questions. So I hope you haven't had much troubles running any of the cells or filling any of the exercises. For the most part, and well, I'm cheating because I have a solved notebook here, as you can see. I have more notebooks than you. Advantages of being the guy giving the tutorial instead of receiving it. So here I already have it full, and I saw that it was running before, but sometimes I've had cases where an IP address gets reassigned in a cloud instance or things like that. So I hope no one has faced any issues. If you have any issues with your IPs or with the hardware in the instances, let me know, and I have a few extra instances running in case you want a new one. And that said, I hope you didn't write much code. I hope you noticed that even for doing things like our hyperparameter optimization, it's a couple lines. A little bit more if you get sophisticated and start seeing what was the performance, and maybe you want a chart, graph it. But generally speaking, let's go through just the quick basics. So as you can see here, we decided to use a few artificial data sets just that they exemplify very well what the point of the tutorial, which is how to use the tools. I would love eventually to give a tutorial more in depth with case studies of cuML and how it has accelerated real life workflows, but that might be its own tutorial on itself. So first, the thing here is that we're going to be using scikit-learn, and might be a good idea to increase the font size. So here, the thing I recommend people is to use scikit-learn version 0.21 and upwards. There were quite a few very nice life improvements, particularly in the next notebook, logistic regression for scikit-learn had very nice improvements. It supports now, if I remember correctly, ElasticNet support in logistic regression is new. If not in all solvers, almost all solvers for logistic regression. And they had a very nice release. But generally speaking, also, this is a great way to check versions even in a notebook. Just always check. It's kind of a sanity check that your notebook is using the library that you're expecting it. So if you notice in the code that I provide in the notebooks, for the most part, I tend to print the version. That is so because sometimes you reinstall packages. The complex packages, as you noticed, have two components, and in our case we have a Python package and a C++ package underneath. Sometimes if there was a hiccup in the Conda servers or some of our uploads failed for whatever reason, there was an issue in the labels in the Conda servers, it might install non-matching versions of the C++ and the Python library. So sometimes you think you're running cuML 0.8 and you run the version is like 0.6.1 and you're like, wait, why? Then you just run conda install again and install the correct one. But little hints of things that, since I've also been very involved with packaging lately or supporting packaging, things that people run into or issues that they tend to raise with us relatively frequently. So I just wanted to mention that little tip, generally speaking. So as I mentioned, the scikit-learn API is very, very user-friendly. I remember it was in recent conference, can't remember which conference was it exactly, but Francois Chollet was one of the keynote speakers, designer of Keras, someone that knows very well about API design, how to make things friendly. You compare the traditional TensorFlow API to Keras, you know that Francois Chollet, pretty good designer of APIs and good things. He also agreed with what I said. Scikit-learn probably is one of the best designed APIs in the data science community overall. It's super easy to use. It's just create an object. In this case, we're going to create our linear regression. And this linear regression is the object that creates the ordinary least squares regression. So it's the most basic. Let's try to fit a line to a data set. Probably the machine learning 101, if you want to call it somehow. Then to fit it, we are going to be using a little bit of NumPy magic just for the data set we created to make it into the format that scikit-learn expects. It expects essentially to be a square matrix depending on how many variables. In this case, we have only one variable, so it should be one column. So this NumPy expand just creates a column based on our x. So if we check x, You see how it's one single row, it just creates a column. The NumPy expand, I'm telling you, hey, and hey, here, NumPy, please expand this into being a single column. So x is gonna, x is gonna be, sorry, y is gonna be modeled as a linear combination of elements in x, which is a single element. So it's gonna tell you, hey, how could I try to fit a line to be this data set? Yes?
Normally you're feeding Y, not Y noisy.
Probably an oversight from me in this solution notebook. Oh. Oversight, totally. Now we have it fit. And that's the nice thing about the API actually. It's very, very easy to iterate and do changes like that. There's, if for people that have worked with Fortran or C++ APIs, you know how much happiness and joy this type of API design brings to your life. If you have told me to change a low-level kublas, CUDA matrix multiplication, that would have taken a longer time. I'm just gonna say that. Then after that, we now wanna visualize our line that was fitted, and now we will visualize a new one that I had here because I had fitted the wrong one I was expecting to. So we're gonna just be using standard NumPy functionality to create a linear space. And then the other main function for regression objects in scikit-learn, we're gonna predict the new inputs. So since in this case, we created a linear space, that means a grid of points, in single line in this case, because it's one dimensional. And then all of a sudden we have our prediction. So in this case, it's just a matrix multiplication underneath, but for a more sophisticated algorithm, this predict can be pretty complex. And now we go simply to, and I just slightly apologize for using matplotlib here and not other things like Bokeh or Seaborn. I prefer Seaborn highly, it looks better, easier, but I didn't want to install more packages in our Google Cloud instance. And now we just fit, we were gonna graph our library. If you notice when you were running the notebook, the slowest part of the whole notebook is graphing the thing. I found that pretty funny. But now we can see that the scikit-learn model modeled or really fit well the line that we had as our Y, not as our Y noisy, in spite of we training with Y noisy. That means that the optimization process that scikit-learn did to minimize the error of the observations to the line that it fit worked pretty well. We cannot see the black line, essentially. That's kind of the objective we're trying. So now we're going to do the same thing with cuML. So as hopefully I have suggested so far, the solution is going to be very similar to the scikit-learn code. There are going to be a few differences, things like if you want to use cuDF data frames, then you are going to create the cuDF data frame. A little cheat that you could have done is that cuML actually accepts NumPy arrays, so you didn't need to do decel, creating the cuDF data frame. But I just wanted to be a little tricky and didn't mention that too much, so people would go through the exercises and create a cuDF data frame. But we're trying to make all the libraries be able to use. Like, I don't want to give people the overhead of having to have the whole rapids if sometimes you just want a fast clustering on top of your deep learning based workflow. So this was my suggested way of creating the cuDF data frame with a simple dictionary that tells which is the name of the column and the values that go into that column. That's kind of my favorite way of creating data frames very quickly if I already have a set of NumPy arrays, for example. Now we have our very nice looking data frame. And similar to what we did with scikit-learn, we will import it and see what version of cuML we're running. This is a very funny bug that a few people already saw. We have a little dirty word there. The thing is that, generally speaking, we use a Python script versioneer, which is standard for generating the version of packages when we release a new version. So when it's built without the user compiling itself, it should say 0.8.0 plus the hashtag without the dirty. The dirty happens if you modify the code and you recompile, it adds the dirty. But it was a little bug in the CI process that made it so that it was modified a little bit and therefore generated the dirty. 0.8.1 or 0.9 should solve that, but don't be scared right now if you see dirty. That doesn't mean your cuML is damaged or anything like that. And now what we need to do is to instantiate our linear regression object and feed it. In this case, it's going to be the exact same call that scikit-learn did. And I hope you find this all very boring and very, because that means that it's easy to use. So if you notice here, I just create a linear regression object now for as linear regression GPU, which is the way I imported my linear regression object. And this is equivalent to using all these default parameters. Just like scikit-learn, we decided to do very heavy use of default parameters in Python so that the user can use the libraries with as much knowledge as he has. So in this case, let's say you are very, very new to linear regression. You don't know that it has options for different solvers. Or why would I need a different algorithm or solver? What does that mean? Well, you don't need to use it. By default, we will do a educated guess of a solver for you. But this is equivalent of choosing our egg decomposition solver, which is our faster solver, feeding the intercept, and then not normalizing the data. And now we just execute the cell, and we can see that now we have a train network. We can now create our visualization for our new graph. Just for consistency, I decided to still create a data frame with our linear spaced base from NumPy. This could have been just the NumPy linear space, as I mentioned before. And now we just do, similar to scikit-learn, the same call. We just predict the outputs based on that linear space. And then we can just chart, adding a final line. So here, this final graph will have the black line, which was the original Y. We'll have the red one, which is scikit-learn. And we'll have the green one, which is cuML. And as I mentioned, this is the slow part. I was not joking. There it is. And happily enough, there's no red or no black line. That means that our green line is on top of both. We had this exact same result, or at least to probably 12 digits of precision, the same exact result as scikit-learn. That said, and I think I put a few notes in the notebook following, we are not actually running the same algorithms as scikit-learn always. Sometimes we implement different algorithms that are more appropriate for GPUs or for massive parallelism. Sometimes scikit-learn goes for a serialized version that is the most mathematically correct, but it can be very slow. And you can choose different solvers. So sometimes you see differences in the results, and you might say, hey, this is wrong, which one is wrong? Well, actually neither is wrong, it's just a different approximation of the result. That's something very important to know, and that's one of the things that you end up playing a little bit when you go from scikit-learn to cuML. Sometimes you need to change which solver you are using or adjust the parameters a little bit if you want the same results. That said, sometimes we get better results with cuML just based on the fact that we can optimize more times. Like if we have an optimization loop, we can run it more times just because we are faster. But sometimes we have to use approximation algorithms that are parallel. And now for the rich regression, I put the diabetes dataset that comes from scikit-learn. I cannot thank them enough for having built-in datasets. It's kind of awesome for testing and for creating notebooks. That's a, I think, 11 variable dataset. And now what we are going to be exploring here is doing hyperparameter optimization. So in the case of rich regression, which is the algorithm that I presented here, just have mainly one parameter you want to play with, which is the strength of the regularization. For other algorithms, you might have tons of parameters. And if anyone has done deep learning, you know that, well, hyperparameter optimization, there is optimizing tons of parameters, depending one per connected node, essentially. So this is the same concept, essentially, but since we have less hyperparameters, we can literally go through all the possibilities sometimes or do a random search and find pretty good results. So as you can see here, this time we did our standard division in train test side of the dataset for correctness. And now we saw here, and here's the explanation that I put, that technically you're running different algorithms in scikit-learn and cuML, even though both approximate the same thing. So here you can see how cuML has three different solvers. We have the eigensolver, singular value decomposition, and coordinate descent. And in the other hand, the only one that coincides with scikit-learn is singular value decomposition. If you choose SVD in both, they are as similar as it gets. There are a few differences in how parallel the implementation is. But if you use eigen decomposition, which is the faster one, and compare it to scikit-learn, sometimes you're comparing apples to oranges. So just it's always something to be very, very aware of. That said, scikit-learn I usually recommend using the solver auto. They have heuristics that kind of choose the best solver for you based on dataset size and other few things. We haven't not implemented yet a solver equals auto for quite a few reasons. One of them is for many more complex algorithms, we still don't have a good heuristic. We want to see more user cases to see what heuristics are going to give the users the best performance usually. So it's not something that we necessarily know a priori. So that's the reason we have, when you call regressions in cuML, it will give you a particular solver. It won't necessarily do a sophisticated selection of which solver. It's already a predefined one no matter what the input is. And now the exercise was to create the rich regression models and feed them and predict them, which as we can see in the code here was kind of, once again, the same thing, a linear regression, but instead of linear regression, we had, I named it as a scikit-learn rich and cuML rich. I put the parameters explicitly myself, just I tend to like that better. But you could have called, without this, just calling the solver to choose a particular solver. For the dataset size, I chose Cholesky in scikit-learn. It tends to be, for dataset was the one that gave me the best accuracy. We just run our cell, and now we can do the same prediction and see what was the accuracy. We use the built-in accuracy from scikit-learn, which is using R-square, which is kind of the squared sum of the errors between the observations and the line that you are feeding. So the lower the value, the better. So we're going to optimize based on that function. Now, the nice thing, as I mentioned, is that we're very compatible with scikit-learn. So we will just go and import the grid search cross-validation strategy from scikit-learn. What grid search does is that you kind of define certain points of the parameters that the algorithm will explore. A grid search literally explores all the combinations of all those parameters. So in this case, we defined a very simple linear space, so a set of uniformly distributed points, logarithmic in this case, using log space, from going from -3 to -1 for the alpha value, just based on experimentation I did before doing the notebook. So this means that grid search will try all the 10 points that we are generating in this grid. We could use the other one, the other strategy, which is random search, that would just look at random points in the space, not necessarily at all of them. Which, if you had a lot of hyperparameters, might save you from running for days the algorithms. So we just define those, and we create our grid search object. We put our rich, which is the scikit-learn rich object. We tell you, hey, what is going to be the optimization strategy? We tell you, hey, it's going to be the R-square score. And then we just feed our model, but we're using the grid object. And if you notice, it gives you a very different output. It's giving you essentially what is the estimator that it used, and it also gives you things like what was the best parameter I found with the best score. So now you can just create our new version of scikit-rich where our found optimization parameter. And finally, the exercise was doing the same thing with cuML. I gave you a very suggestive hint. You don't need to create a new grid search or do anything manually, like iterate through all the values of the parameters, which is valid, but more work for you, and that is not the idea. So we just can call the same grid search CV from scikit-learn, send the cuRich object with the parameters that we're exploring, the same score, and just do the same fit with xtrain and ytrain. And as you can see, it processes it without issue. It gives the same warning that it gave before, which is just from upcoming deprecation of a value. But generally speaking, it works exactly the same. I think right now, almost every method from cuML except random forest and logistic regression are compatible with this hyperparameter optimization. 0.9 will have those two also be compatible. And the second exercise that I put was a logistic regression, which I won't go necessarily into much detail because it was essentially the same thing as the linear regression, just with logistic regression. I will just emphasize the main difference here is that we were not using NumPy inputs, we were using CuPy inputs. For people that are not familiar with CuPy, CuPy is a very, very cool library that is essentially NumPy in the GPUs. It's the same API as NumPy, but it's using CUDA underneath to create an array. So they even suggestively suggest that they even very suggestively mentioned that you could import CuPy as a CP, which is remind us of NumPy, import NumPy as NP, and then you can do the same type of operations. And you can create a range with arrange and do the reshapes and do the as types. So CuPy is a very, very cool library that I recommend using a lot. But the point of this exercise was showing you, hey, what if I already have another library like PyTorch or CuPy workflow, and I want to use cuML. So here the idea was to use the CuPy arrays as if they were the same thing as the NumPy arrays. So the main part here was feeding the scikit logistic regression, which some parts you would need to transform it to NumPy. So in the actual notebook, I think I added a hint of, hey, CP as NumPy gives you a NumPy array from a CuPy array. So the idea is to create your scikit-learn classifier and send the NumPy arrays from the CuPy arrays. That was so in this case, it was actually harder to use the scikit-learn estimators and the cuML estimators, in which, oh, that was a wrong cell. Here in the cuML logistic regression, I just, there it is, sorry. As you can see, this was my Scratch notebook where I have the code, but here in my cuML logistic regression, you can see I can just send our X-train and Y-train models. Now, an important thing that I mentioned in the notebook is that you have to be careful with which data types cuML expects. If you just send Y-train as it is, Y-train was an integer array, and cuML wants you to have everything be the same data type. So if X-train was double precision, so np.float64, Y-train should also be np64. So here we just use the CuPy functionality to make it numpy np.float64 without much needed before that. That said, this functionality will improve significantly in 0.9. We're making automatic conversion of data types part of cuML. That's a pull request that should be done this week. So next week, if you pull the nightly of cuML, you won't need to do this Y as type. It will just automatically convert your memory to the correct data type, and it will warn you that it will use additional memory. That's another thing that we're trying to be very careful about, informing users when we use extra memory because the input was not ideal, or if there's like an additional penalty being done because you send things that are not in the way we expect them to be. We deal with it, but we tell you, hey, it might be faster if you didn't do it this way. And that was kind of the crux of the exercise, just creating the same thing we did with linear regression, with logistic regression. And finally, we have the UMAP exercise. Just for the sake of time, so we can go into cuGraph, I just wanted to ask if people were able to go through the UMAP notebook. So I see roughly 70% nods yes, 75% nods yes, and a few nods no. The notebook will be posted in the GitHub repository, and it will be in the Scipy repository and also in the RAPIDS notebooks repository. But let's go through the solved version. For people that, if you notice here, this was in my workstation, not here. So if you I run an NVIDIA SMI there, I have different GPUs. If we run it here, we actually change and we have our Turing T4 GPU. Now, I won't run it necessarily to give you some time for the cuGraph notebooks, but the solved exercise in the notebook was studying the dataset of digits of MNIST, which essentially has 10 types of objects in the dataset, which are the numbers, the handwritten numbers. And then each handwritten number is essentially a 26 by 26 or 28 by 28 image, which is essentially one single array. So if you to graph it, actually we have to reshape it. And therefore, for a machine learning algorithm, this is a 28 square number of dimensions array. It's not an image per se. So it's relatively high dimension, number of dimensions. So if you had to graph it like a scatter plot, that might be a little bit challenging, because how do you graph a scatter plot of 28 dimensions by 28 dimensions, or 28 square dimensions. So it's interesting, and this is the moment when we use techniques like dimensional reduction to go from 28 square number of dimensions to 2 or 3 dimensions to be able to visualize data sets. That said, it's not as easy as we just remove all the dimensions and we just keep the 3 better ones. Well, what do having the 3 better ones mean? And you're just removing the information. So there are many algorithms that have come to try to solve that problem. One of them is TSNE, and the other one is UMAP. And there's also PCA and others. But what they do is they model in the high dimension that they make assumptions of how the data is distributed in a higher dimension. In the case of UMAP, it essentially assumes that it's kind of uniformly distributed in a high dimension donut, for lack of a better explanation. And then that donut essentially projects it into a plane, or kind of puts a light and projects the dots in that donut into a lower dimension plane, and what we see is kind of the shadows of the dots in the donut in the higher dimension. Without going into a lot more depth, I think that's the best way I can think of explaining UMAP, but it's a very, very cool high dimensional geometry properties just to be able to reduce these 28 square dimension arrays into a visualization that looks something like this. In this case, this comes from TSNE, which just assumes a different distribution in the high dimensional world and does a different projection. But what they do is, let's say we didn't know these were the digits beforehand, they will be able to detect that there are certain clusters and certain things, and you will be able to visualize and see whether there are relationships or not. Now, this comes from a pre-release version of TSNE from cuML, which is still a work in progress. But the pull request, you could even go to our GitHub as in progress, and you could even build it if you were very interested. But the idea would be to see, hey, if this is what TSNE does, what would UMAP do? Like, TSNE is already pretty good. Like, it reduced our space into these 2 dimensions, and it was pretty, not a bad image per se. It looks nice, right? So as we mentioned before, we're gonna use UMAP, which is not available in scikit-learn, but the official package, or the de facto standard package, is called UMAP Learn, which has the same API as scikit-learn, which is kind of a topic in machine learning these days. So this comes from the UMAP Learn package. We just import it, and we just create the object. The 2 particular parameters we're using here is number of neighbors, which at some point it does a nearest neighbor search in its high dimensional donut. This is one of the hyperparameters you would need to optimize to be able to create significant clusters or a well-looking visual. And the other is we're using an initialization strategy. So as you can imagine, it has to start somewhere when it tries to calculate how many different types of clusters there are. This is doing an experimental initialization called spectral, using spectral clustering. So it does a pre-algorithm itself, does that initialization, and I silence the warnings in the notebook I put in the container. But if I didn't silence the warnings, you could see all these warnings. As I mentioned, that Ninity spectral is kind of experimental a little bit. I was not joking about the warnings. And if you run that cell, well, you probably waited for, I think it was 1 minute 40 seconds, roughly. That was not fun. So I won't run it because it would be very awkward. It's very awkward to be 1 minute 40 seconds waiting for a cell to run while you're talking, by the way. But then you went and the exercise, well, hey, let's do it with cuML. So we just create a cuDF DataFrame. Well, I have not run the cells myself here, so sorry for that. But then we do the same call to cuML UMAP in this case. We have the same parameters. We support pretty much all the same parameters. Might be all of them. Can't remember off the top of my head. And then if you run this cell, you saw that I think the runtime of this one was 9 seconds. So you went from 1 minute 40 seconds to 9 seconds, which is not as awkward to stand here in silence in front of you. It's much better if you're giving a small tutorial lecture. And then if we just graphed it using a few matplotlib looking calls, which matplotlib is still not the prettiest library ever, but it does the job efficiently, and it's a very flexible library at the end of the day if you know how to use it. And as you can see, the visualization that it creates is very, very different from what we saw at TSNE, and in many senses is way more informative. If you notice here, it's very interesting to see which clusters it's put together. I found that fascinating here that you can see how it puts 7 with 9 with 4. And you can see those are slightly similar. And then you can see how here it put 3, 5, and 8 together, which are kind of bulbous with almost 2 circles type of digits. So if you notice here, it's a lot more rich interpretations you can take from the visualization. And you can imagine how you had different data sets, for example, from patients with multiple variables. It might reveal more interesting things in a visual manner. I'm very much a visual person, so I think it enhances the intuitiveness of work immensely. And now the exercise that I won't run because it runs a little even slower in CPU UMAP was to create the same thing but for the fashion MNIST dataset, which if you notice instead of digits are just low resolution images from boots, dresses, shirts, and other objects of fashion. So if you run the notebook, eventually you would arrive at something that looks like this, which if we go back to our TSNE example, which, I mean, it kind of separates the things, but it doesn't look that amazing in comparison to here, where at least from an aesthetic perspective is way more interesting. And once again, it's very interesting to see what things did it confuse. And particularly, it confused shirts with dresses, which if you think about it, is like a dress is kind of a long shirt. So I'm not too surprised. So it's very, very cool to see what things you can deduce from the visualization from UMAP. It's a very, very cool project, and people have used it to visualize things like the weights from a very, very deep neural networks and see what activations happens and how things change based on the visualization. All of a sudden, you have higher interpretability from deep learning, which is kind of pretty big topic these past couple of years. And I hope you see the value of cuML going from a minute, 30 seconds to minutes to the time of 10, 20 seconds. You could iterate through a number of neighbors, so you could create a better visual, like 15 times before you could run a single time in the CPU. So that's the way it can really enhance the results you achieve before a deadline that is coming pretty soon, which is always the case. So that was kind of the introduction of cuML. I know that there was a significant amount of time, but the thing now we can do the last 20 minutes with the cuGraph, and I will mainly let you play with the cuGraph notebooks, which are mainly they're all self-explanatory in the sense that they're all solved in the notebook. In there, we kind of predicted, or we kind of modeled and fit and predict our models to there would be a significant amount of time of distributing the instances. It is always a challenging thing to instantiate 80 things in the cloud and give you IP addresses. We'll get a better solution one day, I promise. But the thing about cuGraph is that it's modeled against Network X, which is kind of the de facto standard. Now, there are a few nodes for cuGraph. This one, for example, is you can only have int32 vertex IDs. That means that you cannot have more than a couple billion number of nodes in the graph. But with practical things, it's probably just graphs of 500 million. I think it's probably the practical maximum. That's being improved to be int64 and remove those limits. And also cuGraph is going from single GPU to multi-GPU. That's kind of the aim. But Network X kind of, even though it's not the fastest implementation of all the graph analytic libraries, it's the de facto standard because it's so complete, it's so reliable, and it's actually a very good, well-designed API as well. So in order to, the thing about graphs on comparison to traditional datasets is that now you have two types of data. You have the data related to the nodes, which you can have anything related to the nodes. The nodes themselves can be a full dataset. So here you can have each node is a person, and each person has name, weight, everything you have in a traditional dataset, but you also have the connection between the people. And those connections can also have information related to them. So for example, what we call weight, which could be how much of a friend you are with a different person. So as you can imagine, it's not as straightforward as modeling matrices as we do in machine learning. Network analytics have a lot of that structure richness to create insights, but at the same time, that's a big complexity. So that could be a tutorial on itself, full 3-4 hours of Network X and cuGraph. So that's the reason we had to make it just an exploratory type of notebook. But Network X allows you to read files, standard files for creating datasets. Differences from cuGraph is that we rely on cuDF to read the data set. So cuDF, one of the great things about cuDF is that it has great input-output capabilities by now. Has a great CSV reader. If anyone has tried to read 10 gigabytes into Pandas DataFrame using Pandas read CSV, well, that's another awkward few minutes. We would be in silence here. cuDF that read CSV is an incredible GPU-accelerated CSV reader directly into GPU memory. And cuGraph relies on that. So in order, for example, to create a graph, it just needs to use the CSV reader from cuDF, create the data frame with source and destination. So source is, as we saw here, source are the nodes, and destination are the nodes that they're connected to. And then we can create what we call a graph object. The graph object contains source, destination, and it can contain things like weight and other things. That graph object is the one that contains our data set. It's not only a variable, it's a full-blown object because it has the structure properties. And we can do a lot of basic operations. Just for speed of showing you that how things work, I just run all the cells quickly, but it's very similar to Network X. The graph object has already a lot of built-in algorithms and properties to the cell, so you can see how many number of connections you have in your graph, how many number of people you have in your graph, in this case, vertices, and you can start playing. So we had a few exercises. I think this is the only full-blown exercise, which is easy, I promise. Very, very easy. I won't click the solution because I will spoil it. And then the two example notebooks that we are showing you, and I will let you explore in the last 10-15 minutes, is the Louvain community detection. Louvain community detection is an algorithm to detect communities, so kind of a typically connected groups of people in a graph. So essentially, it's trying to find groups of friends. It's very, very well behaved, very interesting, but it's pretty complex regarding computational complexity. So it's something that we get a lot of acceleration from. So the example notebook shows the same simple graph, but ends up finding these friendship connections, which from a beginning it might not be as obvious of how mathematically would I find those connections. Louvain is very good for that. And the other example we show is kind of the poster child of network algorithms for the past 15 years or so, Google's PageRank, which has, well, I won't go into the story of PageRank, but massively important algorithm for Google search and a lot of other applications. PageRank in cuGraph is massively faster than NetworkX. And it's also just as easy to use. So the example goes through how does PageRank work for NetworkX, and then how does it work for cuGraph. There are a few differences. So just before stopping, cuGraph is coming together. It has a lot of coming things, and it's incorporating a lot of projects. It includes things like Hornet and NVGraph, and things are coming together into a single project. So it's kind of a very complex network itself. So the network library is kind of a network, which is very appropriate. And then things are growing very fast as well in the network analytics tool. And it's interesting to see how it diverges in type of functionality from the machine learning capabilities. So without that, I will give you the last 15 minutes to play with the cuGraph notebooks, and if you have any questions, or if you want to run the UMAP notebooks and you have any questions, please let us know, and then thank you for listening to my ramblings about UMAP.